Hello, everybody. Welcome to this after lunch talk. I'm glad I was able to draw some of you away from the illustrious speaker in the other room. Just before I get going, I'd like to know who here has done functional programming before? Statically typed functional programming. Okay, great. You're in the right place. If you hadn't done that before, then this talk might be difficult to follow. I hope that I've made dependently typed functional programming accessible for all of you. And if I fail to do that, I apologize in advance, but I'm really doing my best. Who in here has worked with dependent types in some sense? Okay, I hope you're not bored. So the goal of this talk is not to present anything new and not to present anything that I myself have created or discovered. Instead, I want to sort of be a conduit between what people have discovered in the past. Some of their identities are lost to the mists of time because there's things that have been sort of folklore and common practice that have been written down later and attributed to folklore and common practice. And I hope that by seeing a little bit of dependent types in action that isn't the standard tutorial, that you'll be able to get sort of a feeling for how it works. I welcome questions about sort of to clarify things underway, but I'd rather avoid long discussions until the end to make sure that we can get to the payoff, because I think that's kind of fun. So I may punt you to the end if you ask a question in the middle. So the topic today is a particular design pattern we get in dependently typed programming called the universe. Before we get to the specifics of how that works, I want to get to a little bit of background. All of the examples are in a language called Idris. We could just well have done them in another language, but I like Idris. So Idris is a general purpose functional language, which is to say we intend it to be a language that you can write the same kinds of programs in that you could write in something like ML or Haskell. At the same time, it has full dependent types, which is to say that the language of the type system and the language of the runtime computation system are one and the same. We don't have a sort of syntactic distinction between what you're allowed to do to the left of the colon and what you're allowed to do to the right of the colon. It's developed by Edwin Brady at the University of St. Andrews, but we have people all around the world contributing, myself included, and you're welcome to become one of them afterward if you think this is inspiring. So I'm going to start off just sort of a little introduction to Idris and some things in dependent types that you may not have seen before. Then sort of talk about universes in this framework of design patterns, sort of vaguely reminiscent of the Gang of Four book. And then walk through 3 concrete examples in increasing complexity. So first off, an intro to Idris. If you want to define a data type in Idris, then it looks a lot like Haskell. So we start off and we say, we're making lists, and a list is something where you give it a type and it gives you back a type. So int is a type, which means that you give it to list and you get back list of int, which is itself a type. So it's kind of like star in something like Haskell. We give it constructors. So we give it an empty list constructor, which is called nil in deference to the wonderful tradition. And here we're saying that no matter what a is, nil is a list of a. So we can have a nil which is a list of ints or a nil which is a list of strings. We can also define the other constructor. Cons is how we pronounce this. It's in parentheses because it's an infix operator, and that's a feature of the syntax. And cons takes an element of A and an element of list of A and gives us back a list of A. So this looks kind of like defining a JDT in Haskell. In dependently typed programming, you define lots of things that look like a specialized version of list. So Idris has some syntactic sugar to make this nicer. If you have your constructors called cons and nil, you can use square bracket and comma notation, which is expanded. So numbers here is then going to be 1, cons 2, cons 32, cons 123, cons nil. But the thing after the colon here in the data type doesn't have to be a type. We can put anything we want there, right? I mean, it has to end in type because we're creating a type. Otherwise, it wouldn't make sense. But we can parameterize our types over arbitrary values. So if we want to make a type of heterogeneous lists, then we can take our list type and extend it with an index, which is a list of types. And the intention is that they are sort of element-wise the types of the elements in the heterogeneous list. So nil then becomes an H list of the empty list of types. And cons takes an element of type T, an H list, which is parameterized by the list of types T's, and it gives back an H list of T cons T's. Note that the cons to the right is the list cons defined on the previous slide. The cons on the left is the one that we're defining for H list. Idris lets you use the same name in lots of different ways, and it uses the types that it expects in each position to figure out which one you meant. If it can't find a unique solution, it complains, and you have to tell it. I can then define item to be an H list of a nat and a string. And now item is the list containing the natural number 12 and the string hi, which is hello in Danish, which is the other language that I often speak. Question? And please get a microphone so that the people at home can hear you. Back there.
So why is the H list of T's and not H list of T?
So you mean why is it it's not T right here?
Yes. Why is the type of the H list is TS and not T?
So
the parameter. So I would think it's a generic type would be T, but the list of T.
Yeah. So this T right here is a type.
Right.
And this T's is a list of types, which are the list of types, which are the types of the elements of the tail of the list that you're constructing. So in this particular case, I have 12 cons hi, cons nil. And so
so it's it doesn't have to be from the same type?
No, it's a heterogeneous.
Yeah, exactly.
Oh, okay.
This is an encoding of a heterogeneous list by telling us which types we have in each position.
That makes sense.
Thanks for asking.
Thanks.
Okay. And when we're doing programming with dependent types, some of our other data types sort of grow new features. I should probably take this phone out of my pocket. So I can write a function where I name one of the arguments, and then whatever value I get for that argument is named by that name in the remainder of the function type. So here we have a declaration of an operator called singleton. And singleton takes some type named t, and then it takes an element of whatever type I gave it, which is to say an element of t, and then it gives back an H list containing precisely one t, whatever t happened to be. And the definition of this is singleton of t of x of x cons nil is what the square brackets mean here. And so then I can go to my fancy Idris REPL, and I can type in singleton nat 42, and I get back 42, which is an H list of nat. And I type singleton string and then a string, and I get back a string, which is an H list containing a single string. So the important thing here is that the argument that we named can occur in the remainder of the type, and that's dependent functions. Yeah?
What I don't understand
microphone?
Oh,
Sorry.
What?
Work? Oh. What I don't understand is the first argument of the singleton function is a t, and the t has the kind type, right?
No. So if you think in kinds, then you'll probably confuse yourself more than necessary.
Okay.
The type of its type is type, which is the type of types.
Okay.
Perhaps that was even more confusing, but type is a type like any other. It classifies the types, and then if you're a mathematician, there's some other stuff you need to know about.
But nonetheless, the type of the first argument of the function is t, right?
No, the type of the first argument is type, and its name is t.
And why is that written like that? Isn't that I don't have an intuition, but like this looks much like the colon type is an additional information for the t, but the type is still t.
So in this case, the t is in fact a type, but it's an argument to the function. So if I wanted to, I could write x colon t as the second argument, and actually name that argument as well.
Yeah.
I didn't do it because there's no x over here inside of the H list.
Yeah.
So if I erased this t colon type, then I wouldn't have any way to refer back to the argument that I actually got.
Okay. So if you didn't need to refer to the t, you would just write type to t to.
Exactly.
Well, you don't have the t, but yeah. Okay. Thanks.
Thank you for asking. Oh, another question. Right here.
Thanks. I'm kind of confused. Where does type live in this case? Is it an element of type itself, like the types of types, or?
So if you've studied a bit of set theory or logic, then you'll know that if that were the case, there would be a paradox.
Yeah.
So behind the scenes, there's a sort of hierarchy of types, like type 0, which contains all the normal types, type 1, which contains everything in type 0, plus type 0 itself, type 2, and so forth. And idris figures those out for you and doesn't show them to you, but it complains if you get it wrong. So that avoids the paradox. And it doesn't complain in a very useful way right now. We need to fix the error message, but we're making progress. So another feature that you see in dependently typed languages a lot, idris is no exception, is this notion of implicit arguments. So if I were to write this is almost a valid Haskell program here, right? I'd need to change the single colon to a double colon, and then it would be a Haskell program. And so we can say that for any type A, it gives you a mapping from an element of that type to an element of that type. But actually what's going on behind the scenes in idris is that it's taking a hidden argument, which is a type, and we're calling that hidden argument A, and then using that in the rest. So to get the identity function at natural numbers, we set A to be nat, and then we could pass it 42. To get the identity function at strings, then we could put in string for A, and then we'd get a string-to-string function. And this curly braces instead of parentheses says to idris that it should try to figure these out for you whenever you use them. And if we need to get a hold of the value that idris filled out there, then in the pattern match clause, we can put curly braces around the name of the argument. So we have this curly brace A, and it's actually not occurring on the right-hand side, so that's kind of a useless binding, but I thought it was good for demonstrating the syntax. Past dependent functions, we also have something called dependent pairs. So a dependent pair is a fancier version of the pair type that you know and love, or the product type that you know and love. And we write this in idris with a double star. And a dependent pair lets you name the first element of the pair and then refer to that element in the type of the second projection. So here we have that answer is going to be a pair where the first projection is some list of types, and we're calling that one t's. And the second projection is an h list of precisely those types t's that we had in the first side of the pair. So if I say that answer is, has a string nat as its first projection, and the answer is, and 42 as its second projection, this is accepted. If I had written 17, then it wouldn't be, because it's using this exact list of types to type check the value in the right-hand side. So at the REPL, we can see that we have two projection functions, kind of like first and second, but we call them get witness and get proof, because this works a little bit like existential quantification. And so we can say that if you want to get the witness out of the answer, that is, get the left element, we get string and nat. And if we get the right element, note that the first element is occurring as part of its type. And that's because we have the name up here, t's, and the name over here, t's. So what a dependent pair lets you do is package up a bit of information and then use that in the type of something else. So you don't have to say, whatever list of t's you give me, I'll give you back an h list. Instead, it's saying, give me some list of t's and an h list for that particular one. And as one sort of final thing, there's a color scheme that we've got from Connor McBride, which might help reading things a little bit later. Because we've only got one sort of syntactic category for expressions in the language, if we want to have useful coloring to help you keep track of things, then we have to do it semantically. So when we color names, red names are referring to constructors of data, things like cons or nil. Blue things are referring to constructors of types, like list or integer or string or type. Green things are stuff that the users defined, like functions, but also just normal top-level bindings. And purple things are bound variables, like from a pattern match or a let binding or something like that. And these colors are a matter of tradition, which is why I'm using them here. I know that some people have a hard time seeing red and green, so if that gets confusing later, please let me know, and I'll tell you what's what. So now that we've got the basics out of the way, let's get some fun code written. So universes as a design pattern. Why do we want them? What problem is this design pattern solving? Well, types are values, right? I can use anything in a type that I can use anywhere else. They're totally ordinary bits of the language. I can write this function item, which takes some Boolean value we're calling b, and if that was true, then it's returning a nat. Otherwise, it's returning a list of nats. And then item true, I can put 42 on the right-hand side, because it's reducing this expression with the value given as the argument. And for item false, I can say 1, 2, 3 for the same reason. So types are values, like normal ones. That means we should be able to write a function that pattern matches on a type. right? Just like we can pattern match on cons and nil. No, we can't. So why is that? I mean, this is something that actually trips people up a lot when they're first starting with Idris. So the first thing, I'm kind of sad Phil Wander's not in the room here. He wrote this great paper called Theorems for Free, which shows how you can use type signatures to know what a function does. So if I see a type signature A to A, then using that technique, I can see that the only function, other than the one that falls into an initial loop or crashes or whatever, like the only total function with that type is the identity. But if I could pattern match on types, if you remember what polymorphic types mean in Idris, it means I've got this hidden argument A. So if I say if A is nat, I'm going to return 42. Otherwise, I'm going to be the identity function. Then I lose that powerful tool for reasoning about what my programs do based on their types. So that would be an unpleasant design decision. Additionally, type erasure goes away. Right? If I'm going to be case splitting on the type, then at runtime, I need to actually check what type does this thing have. And that means we need to have some runtime representation of types. And this is pretty painful when your types can be pretty big. So the universe pattern is a way of solving this. If you need to pattern match on types in some particular domain, how do you do it? So the canonical solution here is to first off represent the types that you want to be able to pattern match on with a data type of codes. So the constructors of this data type are coding for a particular type, in the same sense that an AST might be code for an actual program that you're going to run. So in this case, we might make a universe of 3 particular types called text, real, and integer. I think the name column might suggest how you might use these particular codes. Then we write a function, an interpreter, which maps these codes to actual real types. So in this case, the interp call is that interpreter. And it interprets the data constructor text as the type string. This is where that coloring gets to be handy. It also interprets real as the type double, and interprets integer in all caps as the type integer, which is not written in all caps. As a convention in here, I'm writing the codes for data types in all caps as well to sort of distinguish them from things that they might otherwise look a lot like. And once you've done that, you can do a lot of interesting things. So let's build on that column example. So this is cut down from a bigger piece of code that I've got. If I might want to take that column universe and then use that to build one of tables. So I say that tables are a type. We don't need a special feature for type synonyms because we can just define an ordinary definition which with a type is the thing that you're filling out. And so a table is then going to be a list of pairs of strings and this column code. So in other words, column names, column types. The interpretation of that is our friend hlist. So what I do then is take the second projection of this pair, which is to say the actual column type, interpret that as a real type, and that's what I get, and that's how I can get the type of a particular column. I then map that over the particular list of string column pairs that I've got, which gives me a list of types, which I then plug into hlist from that first example. And now, given data, we have a type, or given that description of data, we have a type that holds that data quite nicely. I can define a schema then. So I can say that a schema for people is, we've got names, which is a text, and then hamsters, which is the number of hamsters you've got living in your house with you, and that's an integer. And then I can fill this out by taking I can represent a relation in that schema as being a list of the interpretation of the schema. So in this case, we can say that yes, there's a hamster in my apartment, and no, there's no hamster in Edwin's apartment. And furthermore, I can pattern match over these things to get useful work done now. So I can pattern match on instances of the interpretation just like I can do any other data type because in the end, it reduces to that hlist type, which we know how to pattern match on because it's got constructors, cons, and nil. So I can count the hamsters in some relation by saying that count hamsters of the empty table is 0, and then count hamsters of a case where we don't care what the name is, but the number of hamsters is h, and the rest is x's. We then add h to count hamsters of x's. And this is a total function. We don't need any other patterns. We don't need to check if this first list here is 3 elements, or 1 element, or no elements, because the type hlist guarantees that it will have precisely 2 elements because our schema has precisely 2 columns. So, but not only can I work at a particular description, I can also work generically over descriptions. I can take in any description and then calculate something based on its interpretation. In other words, I can regain the kinds of things I'd want to pattern match on types for. So let's say I want to print out the result of a query to my database. I can then write a function that prints a header for it, and that takes a schema, and it returns a string. And what that's doing is it's taking the first projection, which remember is the column name, sticking a bunch of tab characters in between, and then concatenating it. I can print the contents of a column by first checking what type of column do I have. So if it's text, then I've already got a string, so I can just return it. If it's real, then I've got a double, which means I need to call some function double to string. If it's integer, then I need to call int to string. And so the type is sort of refined by the reduction of the interpretation. So this interpreter runs on the code that I got from my first pattern match to get the type of the second element that I'm pattern matching on. I can print a row the same way. I look at the schema, and I see if the schema is empty, I know the row is empty, so I return the new line character. If the schema contains some column type t, and then some more columns, then I know that there's going to be an accessible value. And so I can use my print call to get that value using the type from the schema, and then I print the rest of the row. And finally, I print my result by printing a header and then sticking together all the rows. And this will work for any type that I can describe there. Idris even has a feature called type providers, which was sort of the first bigger project I did in Idris, which is where you can run side effectful programs during type checking. So you can connect to your database server, compute the code describing the schema of your type, and then pull that in and type check things based on it. So it's heavily inspired by F# type providers. But the difference here is that you're not having to do any code generation. You're not slinging ASTs around and violating the abstractions of your language. You're running the exact same I/O action that you could use at runtime to get a hold of the schema of a database. So it's a bit different there. So the next little demo is a very simple domain-specific language, which is one for a calculator. Woo. So we can use a universe to construct a sort of an expression type, or an expression type with types. So the types of our expressions are going to be int and bool, and our interpretation will map those to the expected Idris function, or to the expected Idris types. Then I can parameterize my expression type over codes in my universe. So this looks a little bit like doing things with a GADT and Haskell, but when you start doing more complicated things, then you can start having interesting computations over the codes inside of the type, and then that becomes a lot hairier to express if you don't have dependent types. So we have a constant integer, which is an int expression. We have constant booleans, which takes a boolean, and it's an expression boolean. Add gives us two integer expressions, or takes two integer expressions of integer expression, and less than takes two integer expressions to a boolean expression. Then my evaluator can take an expression at type t and give back whatever the interpretation of t as an Idris type is. So the constant integer or the constant boolean, if we interpret their code, we get back integer or boolean, respectively, and we know that the thing inside of the type is correct, so we can return it. In the case of add, we can figure out what the types are based on the interpretations of the codes inside of the left and the right arguments, and so we can just add those together. We don't need to do any more work. We don't need to do any runtime checks or anything. And for less than, the same argument applies. And finally, I want to get to the example that I think is really fun. So the goal here is to describe binary data file formats using a universe once and for all. So we define this universe of formats, and then these are the codes, right? And then we interpret these codes as types, because we're using this universe design pattern. And we're doing this in such a way that invariants in the binary file format are expressible in the universe. We can then write generic binary I/O procedures. So if I have a description of a file format and a file in that format, I can read that in without having to rewrite the file reading code for every single format, and the same for the output code. And we do this by pattern matching on the codes, just like you saw for the SQL example. And I didn't actually write this particular example. It's from this really cool paper from ICFE 2008, back when dependent types were sort of not the barbarians pounding at the door of Haskell that we are today. Sort of back when it was a distant threat on the horizon. And the paper sort of goes through a lot of really cool things you can do in Agda. And I highly recommend reading it. It's readable and great. So the image format that we're going to describe here is called PPM, and I'm using PPM. I was going to do something more fun, but it just gets to be too much for a slide because like Windows bitmap files have all sorts of complicated things in the header, whereas PPM is like the simplest binary image format you can find. So here's a vastly zoomed in picture on the screen, and above is its representation as PPM. So we start off with a magic number, which is P6 in ASCII, or hexadecimal 5036. Following that is actually a width and a height, and these are encoded as ASCII in PPM.
Because why not?
Well, it's because PPM started off as an image format that was easy to email back when attachments were unreliable, and so there's an ASCII version of the format and a binary version of the format. We're working with the binary version here, but the headers are the same, except the magic number. So here we have 3 and 2 as their ASCII codes. If you note that, and then the next is the number of colors per component, and that's 255. I've never actually seen a PPM image in the wild that doesn't put 255 here, but yeah.
So PPM can only be... Sorry, but is there some kind of a delimiter between the width and the height?
Yes,
Sort of when,
that's the next step when I push right on my keyboard the next time.
Okay.
Thanks for asking. Yeah, so there's one or more ASCII whitespace characters, actually. But importantly, after the number of colors, you have precisely one ASCII whitespace character. And I didn't realize that when I was doing this first, and I got some really weird results. And after that, you have the pixels, right? So each pixel is given as 3 bytes. So we have a black pixel, we have a white pixel, a gray pixel. All the HTML people in the room are recognizing how these look. We have a red pixel, a green pixel, and a blue pixel. So the idea is to take this format and describe it in a general setting rather than write a bunch of specific code for every format. So the way it looks in this universe of format descriptions, at the top we have the same file again. So first off, there's the magic number. So we say that we have a part of the file, which is called the magic part. And that's this byte followed by this other byte, followed by some number of white spaces. Following that, there's some number of ASCII digits, and then we skip some white spaces. And this other argument to white spaces right here is there because when we want to use this universe both for reading and for writing. And if we just threw them away, like a normal skip might do, then we wouldn't actually know what to put there when writing it out. So you have to give it sort of a representative to put in when writing, in this case, a single space character. And then there's some number of digits. And these are being named X and Y. I then compute a width and a height, because those were sequences of ASCII characters, and we need actual natural numbers, so I use this readNat function that I wrote for that. And the interpretation of things using this code are those dependent pairs you saw, which is why we need the getWitness. I then can read some maximum number of colors as some number of digits. Read that as a natural number. Yeah?
Just a quick question. I don't quite get why we have to use dependent pairs here. Why can't we just say skip white spaces in a list of, just list of 20 hex? Why is the dependent pair here?
So the reason the dependent pair here is used is not due to the white space skipping. It's due to the fact that the interpretation of the constructor that we're getting from using this bind operation is a dependent pair. And can I delay this a little bit until I show the definition of the data type? Because I think that will answer it. Right. And if it doesn't, then I'll return to it. Thanks. Yeah. And then finally, I skip one white space character. I have a part that I'm calling the image data, and then that's going to be width times height times 3 bytes. Note that width and height here are the actual values that I've computed by reading the width and the height from the file. So that's very important for PPM to work correctly. So that's enough slides. Let's go to the let's go take a look at some real code. So here's that definition of ppm from the slide. We've got the magic number, we've got our x and our y, we've got the width and the height computed from them, and so forth. Given that, result of is the interpretation function for this universe, which you'll see the definition of in a bit. So I can then write a function that'll rotate a ppm image by first saying that it's a function from the result of the ppm data type to the ppm description to the result of the ppm description. Then so the reason we need the dependent pair here when we're interpreting the data type is we need to store what the height and the width were, but we need to have those available in the types of the rest if we want to ensure those invariants. So then we have this make section here, and that's the result of that part. So we get the magic number, we get the width, we get the height, we get the max number of colors, then we get this section image data. If I change this and get rid of the colon, and then ask Idris to check it for me, Idris gets sad. And this is because the type system is ensuring that on the left-hand side when I pattern match, I put the exact right string. So I can sort of ensure some code readability by defining these part names. So I'll put that back. And it type checks again. So the left-hand side, I'm projecting these out, and then I get these pixels. And then what I do is and pixels is of a particular kind of list where the type includes its length. And so then we know that this is the right number of pixels by the right number of pixels. Transpose switches those. So note that on the right-hand side, I switched the height and the width as well. Because if I didn't do that, I'd get corrupted data. I'd have the right number of pixels, but they'd all be lined up wrong if the image wasn't square. And if I happen to write height here, this is also a type error. This one's somewhat less pleasant. One problem with a lot of talks on dependent types is that people never actually run their programs. They get it to type check and they say, yes, ship it. I'm not going to do that. I'm gonna actually show you a running program here. So I can define some of the typical stuff you need on a little command line app, like a usage information printer. It needs a ppm file and an output name as arguments. I have something to read the arguments where it's returning a pair of strings. So I get the arguments to the function. Like C, we get the name of the program as the first one. So we have input and output files. Otherwise, we print the usage and bail. Then what main does is it gets the arguments. It slurps the contents of input into an array of size k bytes. If it failed to read it, then we bail and print the error message. Otherwise, we read in the array. We then read that according to the description of ppm. So this is that ppm code described up above. We then print processed. If this works, we call the rotate function and put that inside of a new array, which is the right number of bytes. And this 10 here is a little fudge factor because sometimes things get a bit bigger if you have a number of white spaces. And then finally, use dump, which takes the contents of a binary array and writes them to a file. So I can compile this. I think, yeah, there it goes. But then I can run the shell command. So I can say, I forget what I actually called it though, so I need to. Here's a picture of me. Let's rotate it. So the file here is called rotate. So I can then say /rotate, and I get back the usage information. /rotate me3.ppm to me_rotated.ppm. It does it, and I see indeed I've been rotated. No clapping. Thank you. So
I think we're all astonished.
Right. So the way that this format description works, we have two universes in play. The first is one of sort of base data, like the small things that we can read. We've got a byte, we've got some number of some other base data, or we've got an array of, or we've got an ASCII character. We can interpret that the way you'd expect. So bits 8 is Idris's 8-bit type. Vect of n of the interpretation of some base type is that sort of list with the type and the length. And characters go to characters. Sections is what I use to get that mandatory string matching. And so what we can see that that does is it takes a string and a type and gives back a type. The constructor makes section, takes some label and some element of A, and gives back a section of that particular label, but just the type A. Right, so we lift the label up to the type level and keep the actual value just at the value level. Then, the format specifiers, we have a part, which takes a string naming the part and the rest of the format. We have bad, which takes an error message. So this is how we say, like, if you get here, it went wrong. So it takes an error message and gives you back a format. End says, we're done, woohoo. Base, which takes an element of that base universe. One of, which is the interpretation to say it's either this format or this format. Many, which repeats a format. Skip, which takes a format. Then it takes a representative, which is the result of that format. Note here that we've got the interpretation function occurring in the definition of the type. This is a feature called induction recursion, which you have in Idris and Agda, and it really makes things powerful. And then you've got the rest of the format. And then you've got this bind thing, which is how I was able to use do notation when I was constructing it. And that takes a format, and then it takes a way to compute a new format from the value read from its first format, and that is itself a format. So when we're interpreting these things, if we want to do a part, then we use section with that label on top of the result of the rest of the format. Bad goes to void. Imperative programmers in the room, this is not the void that you know. This is an empty type, which cannot be constructed, which is to say that you can't write a function that returns the result of the bad format. End is unit, which is kind of like void, the void that imperative programmers actually know. It's got one trivial constructor. Base, we simply delegate to the base type's interpretation. One of, it goes to either, which is left or right, so it's one of these. Many gives us a list. Skip, well, it skips something. And bind is giving us back that dependent pair, right? Because we have that value that we pulled out the first time, and then we have the result of the format that we computed from the value that we read from the file already. And that's where the dependent pairs are coming in. Did that make more sense now? Okay. Yeah. So, just to wrap up.
Wait a second.
Yeah.
There was you demonstrated that if you swap dimensions, then it won't compile. Where is this invariant encoded?
Yeah. So that was coming from the interplay between the interpretation of this bind constructor and the interpretation of this n times constructor of the base. So the bind gave us a dependent pair of a natural number and something with that natural number in it. And this type, vect, is a list of precisely that many elements. When I switched them, those didn't match up anymore.
So you store the binary data by rows, right? And then when you
I did what?
How do you store the binary data? Is it stored by rows or it's stored by like?
So in this particular example, I wrote a little thing that uses the CFFI to like malloc a chunk of memory, and I just hold that. And I walk a pointer down it when I'm reading it in. And the result of processing it is going to be a nested sequence of dependent pairs or other constructors as determined by the interpretation function result of.
Yeah, I don't get it, but maybe I'll ask you later.
Okay. Right, so I'm at the level of summary now. So if you want to do your universe pattern, you have a data type and an interpreter of that as types. You can use these codes for both runtime and compile time computation. You can use it to type check, but you can also use it to make things that work for any type described in some universe. You can use induction recursion to have really expressive universes, like the one we just saw. And then you can use Idris type providers to compute the codes in some universe using side effects and get them from the real world and interact with something outside of your ivory tower language. Thanks very much for listening. We have time for some questions in addition.
So in the main function, you said just allocate some memory with some fudge factor, and that's a little bit worrying in a language that you're trying to verify properties about.
Well, I'm trying to verify things here, right? I mean, I'm using dependent types you can use as a logic to prove a lot of things about your program if you want, but you can also use them to make programming more fun. I mean, there's sort of the dour, the dour utilitarian approach to dependent types, which says, you know, we must prove everything to some spec. But in this case, it's actually saving me work. I'm using it, you know, and it's nice that it catches some bugs, but I don't have to sort of verify everything, right? And if I wanted to put in a lot of work, I could also have computed how much space I actually needed, but I didn't think that was worth it, and I think it would have made the example much harder. So I could actually traverse the description and see what size all of, so the fudge factor is necessary because we have these representatives inside of skip. And so I could traverse it and see what the size expected by all of those are for the particular format in question. If I wanted to prove that was correct, I'd have to probably spend a few hours doing that, but it would be possible. Yeah. So I guess the message is that you can be as formal as you want if your language has dependent types. You know, you can go like total type theory astronaut mode, and you can also sort of use them in a couple of places because it's nice, or anywhere in between. Yeah. Oh. We actually had one more question before you all run off.
Sorry, this isn't really about the formatting. I was just wondering does Idris have like the existence operator that Agda has, where the dependent pair, but you don't have to specify what the witness is. It just infers what the type of the witness is from the proof.
So we don't have syntax for that, but you can write it.
Cool. So the inference would work.
So pretty much all of the things that have fancy syntax are sugar for some underlying name. There's an underlying type constructor that's just called sigma, which is what the double stars map to. And you can put an underscore as its first argument, and then it'll work it out. Also, in runtime programs, you can put underscore star star something if you want. And you can define an alias that did that for you.
Hi. Is there any way to make Haskell libraries available in Idris?
Not in an easy way. I think it actually would be a very difficult problem to do an Idris to Haskell FFI. For one, Idris is strict by default at runtime. So most of the idioms that work well in lazy libraries will not work well in Idris, and vice versa. So probably an OCaml FFI would make more sense than a Haskell one. And even then, if you want to get the types to match up in a nice way, you're going to have a lot of difficulties because a dependent type system isn't just a sort of strict superset of a Hindley-Milner styles type system. They're sort of quite different beasts. So I think it would be, you know, you could make it happen, but it would take a lot of work to make it sort of the nice, seamless experience that you'd want, and type safe.
You think even having libraries from OCaml without any additional dependently typed enhanced features would still be difficult? Yes.
So if you have like a polymorphic type, for example, there's not necessarily an easy way to map that to a dependent type. You know, because you're not just wanting to call OCaml functions that are type nat to nat to nat or int to int to int. You're wanting to call functions that are, you know, list of A to list of B to list of AB, for instance. And if you're going to do that, then you have to get all of the type instantiation rules and encode them in such a way that Idris can check them nicely for you. So I'm not saying that it's impossible. It's just something that would be a quite large research effort to make work well. The default backend has a pretty good C8 FFI, and then the JavaScript backend has a JavaScript FFI. Good.
Just a quick detail question. I spotted some keywords that I couldn't make sense of. One was like mutual, and the other one was, I think, covering or something like that.
Okay, so
what's that all about?
Idris processes definitions from top to bottom in the file rather than having everything be mutually referential by default, like in Haskell. So if I want things to be able to refer to each other and be mutually recursive, then I need to put them in a mutual block. So in this case, it allows the name result of to be available in the definition of format, and the name format to be available in the definition of result of. And then that ends after this indented block. And covering, So Idris has what's called a totality checker, which checks all of your functions and tries to prove that for all type correct inputs, it will return an output in finite time. Not necessarily a short finite time, but and you have to pass the totality checker if you want to use the function in a type, because otherwise the logic would be inconsistent because the infinite loop inhabits every type. What covering does is it relaxes that restriction such that you're allowed to have infinite loops, but it still checks so that you matched all the patterns. So you get a coverage checker more like what you get in something like the coverage warnings in GHC.
And as a second question, which is maybe a bit of a broad question, but still goes through my mind, is that I find all of that quite interesting and pretty cool, and could very well see myself like playing around with it.
Yeah.
But what I'm thinking is like of all those millions of Java developers right now who would a lot of them, if they looked at something like that, it would scare the living hell out of them.
Yes.
So I'm wondering like where do you see dependent typing in the future, like in a way that where can there be a middle ground sort of where we can like move the languages that we have right now towards that direction?
So I'm not necessarily convinced that we should move the languages we have right now toward that direction. It's an interesting thing to try, and you can do a lot of cool stuff, but it gets really scary really fast. I don't know if dependent types ever will be a mainstream programming language feature. I think making them it's really the kind of thing that infects everything about what you do with the language. And so this is my personal take on it, is that if we want to be using it, we need to design it into our languages from the start. And if we want other people to use it, then we need to get better at communicating about it and explaining how things work, and be better at admitting when we're not there yet. And we're not there yet. We don't have mature compilers and runtimes to the extent that you do for things, for languages like Haskell or OCaml or Java or Scala. I hope to get there at some point.
So I guess you would also say that if people want to use dependent typing, they should not try to shuffle it into Haskell, but they should just use Actor or
Oh,
Idris
no, sorry. I think trying to shove it into Haskell is cool, and I want to see how that goes. The jury's out, in my opinion, as to whether or not that's going to be something that's broadly useful for a lot of people, or whether it's going to be something that's narrowly useful for a few people. I'm looking forward to playing more with it, but it's, this is still research, and we're not done with it yet.
Okay, cool, thanks.
Thank you.
We're out of time, unfortunately, so...
Find me in the break. Cons is how we pronounce this. It's in parentheses because it's an infix operator, and that's a feature of the syntax. And cons takes an element of A and an element of list of A and gives us back a list of A. So this looks kind of like defining a JDT in Haskell. In dependently typed programming, you define lots of things that look like a specialized version of list. So Idris has some syntactic sugar to make this nicer. If you have your constructors called cons and nil, you can use square bracket and comma notation, which is expanded. So numbers here is then going to be 1 cons 2 cons 32 cons 123 cons nil. But the thing after the colon here in the data type doesn't have to be a type. We can also we can put anything we want there, right? I mean, it has to end in type because we're creating a type. Otherwise, it wouldn't make sense. But we can parameterize our types over arbitrary values. So if we want to make a type of heterogeneous lists, then we can take our list type and extend it with an index, which is a list of types. And the intention is that they are sort of element-wise the types of the elements in the heterogeneous list. So nil then becomes an H list of the empty list of types. And cons takes an element of type T, an H list, which is parameterized by the list of types T's, and it gives back an H list of T cons T's. Note that the cons to the right is the list cons defined on the previous slide. The cons on the left is the one that we're defining for H list. Idris lets you use the same name in lots of different ways, and it uses the types that it expects in each position to figure out which one you meant. If it can't find a unique solution, it complains, and you have to tell it. I can then define item to be an H list of a nat and a string. And now item is the list containing the natural number 12 and the string hi, which is hello in Danish, which is the other language that I often speak. Question? And please get a microphone so that the people at home can hear you. Back there.
So why is H list of T's and not H list of T?
So you mean why is it it's not T right here?
Yes. Why is that?
It's developed by Edwin Brady at the University of St. Andrews, but we have people all around the world contributing, myself included, and you're welcome to become one of them afterward if you think this is inspiring. So I'm going to start off just sort of a little introduction to Idris and some things in dependent types that you may not have seen before. Then sort of talk about universes in this framework of design patterns, sort of vaguely reminiscent of the Gang of Four book, and then walk through 3 concrete examples in increasing complexity. So first off, an intro to Idris. If you want to define a data type in Idris, then it looks a lot like Haskell. So we start off and we say, we're making lists, and a list is something where you give it a type and it gives you back a type. So int is a type, which means that you give it to list and you get back list of int, which is itself a type. So it's kind of like star in something like Haskell. We give it constructors. So we give it an empty list constructor, which is called nil in deference to the wonderful tradition. And here we're saying that no matter what A is, nil is a list of A. So we can have a nil which is a list of ints, or a nil which is a list of strings. We can also define the other constructor. Hello, everybody. Welcome to this after lunch talk. I'm glad I was able to draw some of you away from the illustrious speaker in the other room. Just before I get going, I'd like to know who here has done functional programming before? Statically typed functional programming. Okay, great. You're in the right place. If you hadn't done that before, then this talk might be difficult to follow. I hope that I've made dependently typed functional programming accessible for all of you. And if I fail to do that, I apologize in advance, but I'm really doing my best. Who in here has worked with dependent types in some sense? Okay, I hope you're not bored. So the goal of of this talk is not to present anything new and not to present anything that I myself have created or discovered. Instead, I want to sort of be a conduit between what people have discovered in the past. Some of their identities are lost to the mists of time because there's things that have been sort of folklore and common practice that have been written down later and attributed to folklore and common practice. And I hope that by seeing a little bit of dependent types in action that isn't the standard tutorial, that you'll be able to get sort of a feeling for how it works. I welcome questions about sort of to clarify things underway, but I'd rather avoid long discussions until the end to make sure that we can get to the payoff, because I think that's kind of fun. So I may punt you to the end if you ask a question in the middle. So the topic today is a particular design pattern we get in dependently typed programming called the universe. Before we get to the specifics of how that works, I want to get to a little bit of background. All of the examples are in a language called Idris. We could just well have done them in another language, but I like Idris. So Idris is a general purpose functional language, which is to say we intend it to be a language that you can write the same kinds of programs in that you could write in something like ML or Haskell. At the same time, it has full dependent types, which is to say that the language of the type system and the language of the runtime computation system are one and the same. We don't have a sort of syntactic distinction between what you're allowed to do to the left of the colon and what you're allowed to do to the right of the colon.